Hello friends, in this webcast we are going to solve another engineering dynamics problem. So the learning goal or objective for today is that we're going to use the concept of 15.4 of our textbook, which is impact. We're also going to use the concept of coefficient of restitution. Basically, this problem involves only this part of impact. And throughout the problem solving, we're gonna discuss what are the logical progression towards the solution, how we're gonna use step by step, because this problem has three questions that we have to find, three unknowns that we have to find using the concept of 15.4, and we're gonna talk about how logically we can move towards the solution. So we will follow a drill for solving a dynamics problem. That is, first read the problem carefully and understand what is asked, what are the given, what are the things that we have to find. So the problem says a pitching machine throws a 0.5 kilogram ball. So the ball is at point A on this image with an initial velocity of 10 meter per second. So it is also shown here. So the ball is thrown at this direction, right, at that direction with 10 meter per second, which creates a 30-degree angle with the horizontal. That's all is given. We are also given some dimensions where the start point of the ball, which is 1.5 meter from the ground, above the ground, and that point is 3 meters away from the wall, and also the dimension from the wall to the rebound back, but we're going to talk about that later. So the given thing are the dimensions in the image, mass of the ball, and the initial velocity of the ball when the ball is at point A. And we also were given the coefficient of restitution. So E is not efficiency here, right? You already know that. So E here is the coefficient of restitution, and that triggers you that you have to use the concept or equation from 15.4, right? So what are the things that we have to find? We have to find at A, we have to find the velocity at which the ball strikes at point B. So we call it VB, and it's in an angle, so we might also have to find the angle at which it strikes at point B. Okay. Next, the problem says if the coefficient of restitution is 0.5, what is the velocity at which it rebounds? So the velocity, we're still at B, but it's the velocity when it's going back. So this is the going in, which is called VB. We're looking for what is going out at point VB, and we call it VB2. Okay, so and then the third one is that the distance from the wall to where it strikes the ground at C. So the part C asks you if your ball is going back, rebounds, and going all the way back here, what is the distance S from the wall to the point C? So how should we start the problem? We have identified our given, we have identified what you have to find. How can we start the problem? So again, for this type of problem, when coefficient of restitution is given, you know that you have to use the concept of coefficient of restitution, and you know the equation from your book, but that is only used at part B. Part A and C still can be solved by the concept that we have learned in chapter 12, 13, and 14. And if you take a moment and consider what is the problem A is, if you will find it's just a projectile motion chapter 12 problem. So that is my plan. I see that problem A, we have to find what is the velocity it strikes the wall. It looks like it's not a straight line. The ball is going hit at point B, so it's a projectile motion. So I'm gonna use projectile for the part A. So I'm going to use projectile motion concept. For part B, it is given the coefficient of restitution is E. So I'm going to use the equation of coefficient of restitution for part B. Again, what should I use for part C? Now you tell me. Right. We have to use, if we look, what's the path, what's happening for C, because it's asked from wall to the point C. So this is the path. And what concept I might use? Sweet. Right. We have to use projectile motion again, or we can, at least for now. Let's assume that we can maybe use. So these are my logical plan that I plan out before I even start solve my problem. So I'm going to use for C projectile motion again, for B concept of coefficient of restitution, and for A projectile motion concept again. So now I'm ready to start the problem. So let's move on and start the problem. So for part A, when we're considering the ball travel from A to B, so A to B, we're looking for VB, right? So it's a projectile motion. What are the basic thing for projectile motion? Whenever we think about projectile motion, what are the things that you think we have learned? Right. The x component of the velocity doesn't change throughout the motion. The y component changes. This is the only thing that is interesting in projectile motion. We have x and y component of the velocity, and remember that this is the strategy of projectile motion, and you can use the concept that the x component of the velocity never changes even though the gravity is acting, because gravity is acting on y direction. So the VBX VAX never change, the velocity in x direction never change. So we can write the VBX, the velocity component, the ball hit. So let's assume the ball hits. Let me redraw it. See the ball is here. This is the ball direction. So it has a x and y component. So the moment the ball hits here, the x component at B will be same as the x component of A. If you understand that, that's what I write. The x component at B equals to x component at point A, which is, because A was 10 meters per second in this direction. What would be the x component? You know it. Cos 30. Sweet. 10 into cos 30, 8.66. It was this direction. It was moving this way. So I put an arrow here marking that it is towards the right. So I found the x component of the velocity from projectile motion concept. Now we need to find y component, because we need the magnitude of the velocity at point B. So how can I find the magnitude of the velocity at point B? Well, if we can find the y component of the velocity A, and we can find the y component at point B. How? What will be the change of VAY to VBY? What are the thing that is causing the change at VB? Ask yourself, what are the thing only acting when the ball is in y component, when the ball is moving from A to B? Gravity, right? Gravity is pulling down. So the change, if we want to find the final velocity, right? So if I write the equation, the VBY that I'm looking for, because if I get x and y, I can find the VB. VBY, I can say initial velocity, that is VAY, minus gravitational acceleration G, and then the time. So to find VBY, I need VAY. I already know. I already know G 9.81. I need to find T. Okay, so I may have to move forward, or maybe I need another more step to find the T. So how can I find the t? What do you think? What should we do? We are in y-axis. To find t, because in curvilinear motion or projectile motion, you have x and y component. If we face trouble in y component, we go back to x component again and try to figure out something. And we also have to check what are the things are given and how can we use them. So you see the distances in x and y direction are given. So since we don't know the height of point B here, so we cannot use the change of position from here to the B, but we know the change from A to B is this 3 meters. So maybe we can use that. Let's see. If not, then we have to figure out something else. But let's see, if we go back to our chapter 12 equations, what is the displacement? S, we say S equals to, here I can say S A to B, S equals to UT, VB or VAX, I can say VAX into T. Why? Because the X component of the velocity in a projectile motion never changes over time, since there is no acceleration or deceleration in x direction. So it's only VAX t, right? So we know VAX. How? This is the VAX. So 8.66, and we need to find the t because it's the same time. The time the ball takes from here to climb up at point B, this height, is the same time where the ball travels from this point to this point, 3 meters. So so from this equation, what is SAB? It is given 3. So if I plug 3 here, I can find T, which would be equals to 0.346 seconds. Now T, we found T already, right? Now go back to our equation and check what are the unknowns. I know T, I know G, I know this part, right? VAY. How? What would be the VAY? Tell me. Think for a second. What would be the VAY? If your VAX is 10 cos 30, your VAY would be 10 sine 30, right? Y component. So if you find that, so you can find VBY. If you plug this value, check yourself. I'm just gonna give you the answer. It'll be 1.6 meter per second, since it's moving upward. So the component direction would be upward. So now, are we done? No, because the question asks the velocity, not the component. So we have to find the velocity VB. So we have the x component 8.66, y component VPY 1.6. So we can use the Pythagorean law and find the velocity VB. So the VB would be this equation, and then if we plug the value of VBXY square, you should get the result 8.81 meter per second. So that is our answer. Are we missing something? Yes, we also have to find the angle it is making from the horizontal, because if I just say VB 8.81, it could be in any direction. It could be any direction, right? So you have to say in which direction it is 8.8. So that's why, that's finding easy. Degree theta 1, if we call it, tan inverse the y component, which is 1.6 over the x component, 8.66, and it will give you 10.5 degree. Calculate yourself. So we figured out this is the answer of part A. So this one and this angle. Now let's move to the part B. So in part B, we have to find the rebound velocity. We have to use, since it's given, the coefficient of restitution. I just go back in your textbook and I just wrote the equation, VB2 minus VA2, VA1, and VB1. What does it means? So if we call the B wall as a B, so let me write it down here. This is my wall, and let's assume this is my ball when it's hitting the wall. So I can call my wall as B and my ball here as A. The 0.5 kilogram ball is as A. So VB2 is the velocity after the impact, and VA2 is the velocity of that ball after the impact. VA1 is the velocity of the ball before the impact. VB1 is the velocity of the ball of the wall B before the impact. So if we look at it, we have to plug the value here. We know E is 0.5. What is VB2? VB2, that's the rebound velocity that we are looking for, right? So I will write VB2 and VA2. What is VA? Wall. Oh, I have to do a correction here because this would be our A and this would be B. It would be much easier if we assume that. So this would be B. Okay, so VB, velocity B of the ball, and VA is the velocity of the wall of the velocity of the wall. So VB2 is the after velocity after the rebound of the ball, and VA2 is the after impact velocity of the wall. So wall doesn't move, so what would be the velocity of VA2? You're right, it would be 0. Similarly, wall doesn't move before the impact, so again we can say VA1 is also 0, right? So this is 0, this is 0, so all we have B1. Now VB1, another thing you have to consider, which is very important in this problem, when you have impact of the ball, even the ball is moving this direction, right? It has X and Y component. Since the wall is flat, straight, is not in angle, so during the impact, you have to understand this, the wall will react only with the X component. The Y component will remain undisturbed. So if you understand that, what it means is that here in this equation we have to say it's VB2, but it's only X component of B. So VB X component of 2. And it's also be VB X component of 1, because like I said, if the ball is reacting with the wall is flat, so the reaction would be straight X direction. The rebound would be a straight X direction. The Y component of the ball will be unchanged. So if we find that, and so what would be the VB X component that we already figured out at the very beginning, 8.66. So we can find the VBX of the rebound, so 2, and if we plug this value, because this is the only unknown, you can find VBX component of rebound, which is VBX2, 4.33 meter per second. What would be the direction this time? Now your ball is coming back, so we're going to say X component is this direction. Now we also have to find the Y component, right? Because to get the VB2, you also need to find the Y component. So VBY component of rebound or restitution, rebound velocity termed as 2. So VBY2. Since we said that during the collision of the ball with the wall, the Y component is undisturbed. If my wall, for example, if the ball was hit with a wall that is inclined, then you also have it will be interacted normal this direction, then you would have component in x and y. Since it's a straight, so the reaction is in only x direction, so y component is unchanged, so vby would be the same as vby2 would be the same as vb y1, right? So it will be the same as it was before or just before impact. So it will be 1.6 meter per second. It's still moving upwards, so it will be upward direction. So if you know this one and that one, you can find the VB2. So just again using this Pythagorean law, if you plug 4.33 1.6, you should get the result 4.62 meter per second. And then you also have to find the angle, because it's not it has the x and y components, so it will be in this angle. So what is the angle is making with the horizontal? This angle. Again, if you do the tan inverse of y component over x component, you should get 20.3. That is theta 2 is the rebound angle. Check your answer after we finish. So now we're down to on the last part, which is C part. We have to find the distance S that is from B to C. Nice. So we again can use the concept of projectile motion. So S, the distance B to C, we can use the component. Which component of the velocity we can use? That will lead us to the easiest simple equation form. Right. We can use the VBX component, VB2 x component, multiplied by the time BC, the time it required to travel from B to C. So VB was the rebound velocity. We're taking the x component, which never changed over time. There is no gravitational in x direction. So if we multiply it by the time required from here to here, TBC, I can find the SBC. Now we know this term. We know what is the VBX. We solved it in previous slide, which is 4.33. But we don't know TBC. How do we find the time it required to BC? Right? Again, we just talked in projectile motion, you have two options, x coordinate and y coordinate. Which coordinate are we in this problem? Right, x coordinate. We're using VBX. So let's move to the y coordinate, and if we can find how much height it moved, and from there can we find how much time it takes from here to be here. So how can we find the height of this height from the ground to B? Let's call it h. What are the heights that we already know? Is there any height given on the problem? Yes, the height from A up to point A is given 1.5. So we have to find just this height from this point. Let me use a different color. From this point to that point. So we can say it is that summation of 1.5 plus something that we don't know. And that was the travel between point A to B. So maybe we have to use the concept that we used at our part A of this problem, and maybe we can get the total height. So I'll write 1.5 plus this term, which would be this height from B to this part, because we know this is 1.5. So 1.5 plus this part. So how can we find the height movement in y direction? H equals to ut minus half. U is the initial velocity multiplied by the time minus, because gravitation is downward and movement is upward, so we put minus negative half g t squared. What time we should use? Should we use TBC, which is this one? No, because that's what we are looking for. This time it will be the time TAB, and that we already figured out in our part A, which is 0.346. G, we already know what G. 10 sine 30, we already know this. TBC is the same. We know 0.346, so we can find H, which would be 2.643 meter. Check your answer. So if we find the height, now we can use this concept, because now the height is from here to here. So that means this is the height it took all the way down here. This is the time it required, so it will be height, the time BC. So if we use that concept again here, we can say for B to C, right, since it's going down, we can say the height is negative, which is 2.643, which can equals to the equation from chapter 12 for curvilinear motion, which is ut half at squared. So ut initial velocity was upward 1.6. T, let me write it down clearly. So yes, so the negative is negative 2.643. This term is the ut initial velocity of, and time is bc that we're looking for, B to C. And what would be the velocity? We're using the rebound velocity, and which component we should use, x or y? Y. So that's why we call it VBY2, the rebound velocity, y component, which is 1.6. Time is TBC, half G TBC whole square, and only unknown is the TBC. We know G, we know this part, so we can find TBC, which would be equals to 0.91 second approximately. So if you find the TBC, all you have to do is that go up and plug here. Sweet. Now can we find SBC? Oh yeah, because we have this one that we already know. We just find out TBC, so we can find SBC. Sweet. So what would be SBC? If you calculate, you will get 3.96 meter. Check your answer, calculate yourself. So that's be the answer of part C. So we have logically progressed towards the solution. We used our logic, we used our concept, the entire concept from chapter 12, 13, 14. Well, we just used chapter 12, concept of chapter 12, and concept of chapter 15 to solve this problem. So in next video, we're gonna talk and solve problems, another dynamics problem. But till then, have a wonderful day. Thank you.